Thank you for your introduction, and welcome to my talk on reactive architecture. So what I'm going to show you today is one way of implementing a reactive architecture with a combination of two of my favorite frameworks that I tend to work with or be a committer in, which is Vert.x and Kubernetes. We already got like a little summary about me. If you have, as he said, like if you have any questions later on, meet me downstairs. Just hit me up if you want to know anything. I'm reachable on Twitter as Code Pitbull. So if you have any questions or things to ask, just hit me up. So the premise, like, why are we talking about reactive architectures in here? I tend to start my talk with giving a little introduction to the problems we've been facing. So I've been working with distributed systems now for more than 20 years. I've run probably in every single problem that is out there. No, I haven't. I discover new ones almost every 2 weeks. But like, there's a basic set of problems that we always encounter. And so now my first question is to you. Oh, I forgot this one. If you're interested in Vertex, one of the other maintainers wrote actually a free book that you can download from the Red Hat page on Vertex if you want to get deeper. It's Java focused, so if you can't stand Java, I like Java still, although I'm almost doing only Scalar right now. Just grab it, it's a pretty good one. So the basic setup. First question to the room. Who in here knows the fallacies of distributed computing? Please raise your hands if there are any in here. Yes, at least one hand. Thank you. So let's get started on these, because I think those are basically the groundwork to understand like what the problems that are that we are facing with today cloud infrastructures. First fallacy, like these are fallacies. These are wrong. Network is reliable. Like if you bet on your production network to be reliable, you're doomed to fail. You see banks fail, most of your hardware fails. Like you have like last year we had actually a fire in a central router system in a data center. Like that's how a network really fails. Like there's still physical stuff in there. There can be all kinds of other things that can destroy your network. Latency zero, my favorite one. This is something that, thanks to the world of DevOps, is getting less and less problematic. The key problem is that many developers only work on their local machines or in a dedicated testing environment, where the latency is actually close to zero, because a lot of the times you're running in the same place inside the rack. That means like the hops almost don't count. So latency is not zero. You share the network. You have cross data center operations. You sometimes have latencies escalating like up to like the several seconds area, even on TCP/IP. Bandwidth is infinite. Awesome. Like if you're like me and have encountered the world of XML and transferring big documents of XML and suddenly having to share your network with 10 other applications trying to push through giant XML documents, you pretty much realize that even a gigabit is pretty dumb if you do not start doing this. So bandwidth is not infinite. And it kind of gets even worse if you're in a cloud environment where you're shared with even more applications than we ever did before. Network is secure. Yep. It isn't. Topology doesn't change. Well, this is like if you have an IP address written in one of your configurations, you're doomed. If you bet on things just being there where they are right now, you're doomed. Like people just decide to do a new network split, like the classic split brain, or they just tend to move things about. Like we just recently had the problem where an admin had the bright idea to reconfigure the DHCP configuration for all servers, and suddenly half of our infrastructure was gone. So topology does change. There's one administrator. This is more of an organizational problem. Like you talk to one person to get a certain firewall rule, and person number two, who doesn't know about person number one, changes that firewall rule back without informing you. So like in big companies, like you suddenly have to take to 5, 6, 7 people who are going to change around things that are going to harm you in production. Transport cost is zero. This is actually my favorite one, and it's only once in my career that I actually hit this one. These nasty little things that actually push the packages out there called network cards. I don't know if you're aware of those, because we ignore them most of the time. They have processors on them. If you're in a what we call a noisy network, high collision rates, or some other weird scenarios kick in, or like we did a fast data project where we had like several hundred of terabytes being floating around in the network, you get to a point where you overload your network card. That's why there are like those expensive network cards that are then bought by companies to help them run their data centers. Transport cost is not zero. There is a CPU running in your network card, and things might just go boom because of this network card. And the last one is like it's getting a little bit better if you're in a cloud infrastructure. but most companies aren't exclusive in the cloud infrastructure. They have Microsoft machines, they have Solaris, they have HP Unix, they have some host systems. There's like all kinds of different TCP IP stacks going around in your system, all of which have their separate different kinks that just make things break. So, lies, all of these. This is like, the problem with these is like, we assumed all the time that these would hold true in most situations, but they aren't. How we're going to deal with it? Well, let's first, like now that we know that things just tend to fail all the time, let's postulate a little, like a dream, like we want to have a system to behave. So, I formulated a little example servers. This is my like, by now it got actually a nickname, it's called the Knight of Resilience by now. Although it was the Black Knight formerly. So we want this guy to insult us to the very, very end. That means like we want the ultimate resilience, like whatever happens to the system, this guy should continue to insult us. Now, when we came to this state, like we're pretty much done for now, like with like classic approaches to resilience. The next part is now, the system is supposed to recover from this state. This means like, now that we are like I'm standing there without arms, like still can insult you, but like I'd like to be back on my two legs so I can give better insults to you. So we can recover from that. And then the next stage is to actually be able to adapt for the future. So this is like these are properties that we expect from our systems and that we want to build in. How? Like how are we going to handle this? Like first of all, it's not rocket science. It's been done since the 50s. Like if you start like me, like looking into old architectures, all the ideas that we're going to talk right now in a few seconds have been around for ages. So this is nothing new. But right now we found the buzzword for them. We slapped reactive on top and everything is good. So let's define reactive. So first of all, like we need a manifesto. Like we are IT people, we only live by manifests. So like that's the first thing we do. If you've been like in Jamie Allen's keynote, you saw it already. The famous one, like we started on top, having responsive. Responsive meaning like I want to be able to give an answer in whatever state my system is. I need elasticity for that. Like elasticity is one of the key things that we have in the cloud and in other areas, because I can only be responsive if I'm able to react to varying loads. Like for whatever reason, those loads vary. They do all the time. Like the most harmful thing you can have in IT is looking at the mean value on anything. You need to look at the peaks. Next part is resilience. We just saw that. Like resilience means like I can gracefully degrade the system. I'm always focused on giving the maximum available functionality to my consumers. The worst thing that I can do is just slap an error message to a consumer. This is like probably a consumer I will never see again. We found the silver bullet for that one. I hate silver bullet, but like in that case it makes a little sense. That we do things message driven. Like the manifesto has changed a little. Like at the beginning there was event driven, now there's message driven. I recommend reading the books from Roland Kuhn, like one of the masterminds from the Acker world, to understand actually what that means. So these all together save the day. So, well, yeah. What does it actually mean? Well, for us, the key implication is that we now have identified a certain set of properties that we expect from a system. And this resulted in the past few years in frameworks. Like we love frameworks, we're IT, again. So like there's now a new generation of application frameworks, like a relatively new, because strictly speaking, who in this room knows Erlang? Or at least Elixir? Yeah, a couple of people. These things have been around since, I think, the 70s or 60s. Like the original Erlang papers have been written, I think, in the beginning of the 60s. So everything we see right now with frameworks, what we got is like more convenient frameworks. Erlang sucks as a language. It's beautiful VM, but it sucks as a language. And we have new frameworks. One of which I happen to be a contributor and maintainer of. Like I'm just like maintainer of the Scalar stack. There's right now a whole team, like it's actually, like most of them are actually paid by Red Hat, because Red Hat is also like, has integrated in OpenShift and everything, so they actually have commercial support for that, which I don't need, because I normally don't only use the open source part. So what is Vertex? Just like the quick elevator pitch, it's messaging based, so most important buzzword in this sense. It has simple clustering. This is a feature I'm going to show you later on. This is like one of the key features I see with like elastic scaling inside a cluster, because Vertex makes it extremely simple to do that. It has an extremely simple threading model. We want to avoid people shooting in their foot. So that's why we restricted the threading model to a big extent. And it has a very small core. I think like the smallest deployment size we have is like around 5 megabytes in a fat jar. That's like I think the smallest you get. It's basically just the core libs and some netty dependencies we have. And we have tons of modules, like from Kafka, Postgres to like whatever hell other things you need, and which are directly maintained by the community. And there's a ton of stuff happening outside the community. So that's Vertex. It's gonna save the day. Well, the problem is like this is just a framework. Like it just helps us. It helps us with a certain style of writing an application, understanding at what areas an application may break. This is like the messaging aspect. It's not only that it couples things, it makes things explicit. Because if I send a message, I instantly know there's no guarantee that there's ever going to be a reply to that one. So, but still, it's only a framework. Well, now the problem is like this is a new slide deck. I messed up my slide deck. So, so this is Vertex. We just forget that I accidentally overlooked this one. How does Vertex do the isolation part? The basic thing that we're going to see later on is a vertical that we built on. Each vertical has one thread assigned to its own lifetime. So it's basically an event loop. It has tons of handlers that are used to interact with I/O, to interact with messaging-based systems, which is going to be the actually event bus. Like it's called event bus, it's actually a message bus, but Vertex is rather old. It's, I think like around 7 or 8 years. Like at that time, people were calling events and messages, mixing up those terms. It's actually a messaging bus. It's called event bus for historical reasons, which means I can have multiple verticals communicate using this event bus. This event bus happens either in memory, just like if you know Akka, like it's built almost in the same way. There are inboxes. There are safe ways of message passing between the verticals. So none of these verticals actually has shared memory with any other part of the application. So all communication happens through that part. The cool thing about this bus is that it does not only reside inside the JVM, it can spread out. So there's auto discovery in there, so machines can automatically connect. So you're not like, you don't, like it's location independent. If you send a message, you don't even know if it's going to be processed on your local machine or on a remote machine. That's decided by the Vertex itself. So you can have like a big cluster, auto discovery, finding all nodes, something that we're going to see running in Kubernetes later on. So, and also another feature, this event bus can be hooked up to C and C++, like there are native libraries for that. It can be hooked up into the JE world. Like I actually had to do this, like I'm ashamed of myself, but sometimes you have to do compromises. So this is like the whole basics of Vertex. We have these verticals, which are our isolation units. They communicate with each other using an event bus. The event bus can scale out and is completely elastic. I talked about modules. So Vertex provides separate, like this list is not current. Like the problem is like keeping track of all the stuff that's happening in the community has become rather hard. So there is already a lot more of these. So like we have like a ton of database connection libraries. There's actually right now a new Postgres client. Then like we have these integration guys. There you see the TCP event bus bridge and those things where you can just hook up to other systems. We have like, there's actually, this list has also grown some while. The list down there is the interesting one. Like that's something we're going to look at later on. Like it's service discovery from inside of Vertex connecting to things provided by your environment. And then we have clustering. So clustering is the part where we have something helping us doing auto discovery for all the node. The classic one is Hazelcast, which has been used from Vertex 1 to right now Vertex 3. We have JGroup support, Apache Ignite support, Zookeeper support, and people are working on other things. So the basic one you normally use is Hazelcast. A lot of people in the faster big data area go Zookeeper because they just have their Zookeeper instances floating around. And then there's like DevOps, like you need the buzzwords. So we have tons of metric support, there's Prometheus integration, all that stuff going on. So, languages, and this is like one of the features how I got into this framework is Vertex is inherently polyglot, which means like we actually have dedicated language adapters for all, not all, like, but many JVM languages, like with the, I just ran out of battery, awesome. Scalar. So like, for that, the interesting part is we went by generating those. So there's like a cluster explosion of annotations inside Vertex for all the core classes. And what we do, we generate the language adapters out of this. This helps us because like in older versions, what we did, like we handcrafted each language implementation. If you look back at the amount of modules we currently support, that's getting quite cumbersome. If you have like this amount of language, you have to go like with like a generative approach. That's why like right now, like we generate all of these, like each of these languages have their maintainers and generate all modules in a language flavor. Like in my case, basically the adaptations happens that you don't see any Java-related API. It's everything completely based on Scala futures and that stuff. So like we really have idiomatic Scala in there. So if you want to get started right now, this is like they created a good rate template, so you can just use that one. Another approach is we have this start page, like Spring Boot is doing it, so we have to do it too. And then we can do these nasties. So like I just sprinted through this. So like we have a nice framework, we have easy to get started, but it has to run somewhere. And this is the part I actually wanted to get to. And now we have these like the nasty old iron standing around in a data center. Does this thing look elastic? I don't think so. And this is like the core problem that we face. The framework itself can help a lot with mitigating certain types of errors, but we expect a little more, especially like when we're going to cloud, even if it's like an on-premise cloud. We expect to have a certain utilization. We don't want to have like these static machines where we have like, we got 8 front-end nodes, we got 16 back-end nodes, and 32 database nodes. Like, problem is like 90% of this CPU usage will be for nothing. So we want to have effective usage, especially when we're going to the cloud. And so having like static servers and manually provisioning them, it's a deal breaker. So what we do is, because you're fancy, is like we use the whale, the Docker thing. Well, yeah. And we dream, oh, that's actually German, like, aha, we got him. Because like that's what everybody thinks. Like I see so many handcrafted solutions where people are like, hey, yeah, we got Docker, awesome. We're elastic, we use Docker. Like you see the question mark popping up on my head, like, because like first of all, Docker is quite the task to keep in production and to maintain. So infrastructures mostly end up looking like this. So like, first of all, like manually tossing around Docker containers is still what many people do. Like there's like a lot of scripting going on. Like I've seen a hell of a lot of shell scripts actually trying to do elasticity using Docker. No, we don't want to do this. So we come to another part, like how can we actually do this to get back to this? Because what we've learned right now is the framework alone can only cover so much. A static deployment of a framework won't really help us with the problems we're facing. So we learn a real reactive architecture, and this is the point we want to get to, is not having a reactive, like, I hate this term, like a reactive programming style. Yeah, oh, I can just slap together a lot of maps, awesome. It's not just having a framework, because a framework can only go so far. It can help mitigate a lot of errors and mistakes. It doesn't, like, the framework can support elasticity, but if the infrastructure is not elastic, how far can it go? So we need the third part, which is basically a combination of a reactive framework and infrastructure. And there are actually like two things, like there's way more out there, but there's 2 infrastructure components I really like to play with. The one I'm not going to show you today is HashiCorp Nomad. I just recommend everyone in this room to just take a look at this. It's really, it's like most work of Hashi, it's like, it's great stuff. It's very low profile because it doesn't even need a container. It can run native binaries and fetch files directly, has cgroups integration. It's very, very low profile. And I'd highly recommend just to take a look at it. As the problem is they don't have the market penetration that the other framework I'm going to show has. So play around with it, test it, see what it can do for you. It's nice. The other one, the elephant in the room, that's Kubernetes. So Kubernetes is like something that has grown tremendously just like within the past 2 years. Like it's from like the roots in Borg and those, it's like we suddenly have this explosion of having it available everywhere. What I want to say is like I like both really, really. Like they're both great frameworks to actually facilitate an elastic infrastructure. So, but today we're going to focus on Kubernetes. Key thing about Kubernetes is just like where you can get it. Like our current project right now runs several hundred machines in the Google Cloud. So where you get like a hosted infrastructure. Like I hate running infrastructure myself. Having a hosted Kubernetes is just great. The other one is Azure. Like Azure also has full Kubernetes support by now. If you go for an on-premise thing, you have DCOS, which is now running also Kubernetes on top. And you get OpenShift, like the new version has been built from the ground up supporting Kubernetes. So really, Kubernetes has become from like a rather big open source project to the lingua franca of infrastructure provisioning, resource management, and all those things. So it's really worth investing your time into this. And the latest player to join the Kubernetes club is actually Amazon. I'm not 100% sure because I'm not currently working on an Amazon-based project, but I think it should be available by now that they have their production-ready Kubernetes support. Like in March or April, they were about to put it live. So we now see we have like the 3 major players in the cloud area. We have 2 of the biggest on-premise cloud systems all running on Kubernetes. And that's all. And then it's like, it's not even a bad system. Like, it's like you get something like JEE running on everywhere else. So like, no, Kubernetes is way better than that. So we actually get to the point where we can do things like this, like where we before had to deal with those monsters on the left and had to manually write bash scripts to provision them. We now have like a very cool thing that we can script, combined with Terraform, combined with everything that we have out there, to have our infrastructure first like automatically created and then have it maintain itself. So now I'm going to dive into the code. I hope I can make it. I got 18 minutes left, man. Just like this is stripped down from a 2-hour talk. If you're interested in what I showed today, it's really just like a very basic example. I tried to condense it to the point where we really just see like what kind of gears are going on in there. This is the code. It's up on GitHub right now. And I'm going to show you, give you a little walkthrough how like the structure of a Vertex application and how it actually internally looks and how the event bus works. So let's go idea. My idea is like I want to implement a chat. Very simple chat application. I want to have as many users be able to connect to this chat, send messages, and distribute it to everyone listening in other chats. So basic thing. Another thing, I mean, like we're living in new Big Brother times. Like I have to like think about like introducing a Big Brother there. So like we also need like some facility that's going to be able to censor the stuff that we say in there. Like, not that we started talking about butterflies or cats or something like that. That's something that we want to keep out there. This is basically the structure of a Scala-based Vertex application. Let's just start from the top. I keep the Scala imports away. The starting point is the Scala vertical. So whenever like one of these gets deployed inside the Vertex runtime, what Vertex does, it associates a thread with this vertical for the whole lifetime. This gives us a few properties here. First of all, you don't need any threading primitives inside a vertical. There's no countdown ledges, synchronized, whatever the hell else you want to use, you don't need it. It will always be touched by only one thread exclusively. Second part is what we call mechanical sympathy. Because if I have a certain area of code that's associated with one thread, I have a very high likelihood that this thread actually keeps the stuff inside the CPU caches. This is very helpful for streaming applications and such things. So I don't have to bother with like the CPU just constantly fetching stuff from main memory. No, like I'm associated with that thread, and if the operating system doesn't get in my way, I actually have hot caches, which means that the application can crunch out a little more performance from my CPU. But the most important property is we protect ourselves from shooting in our foot. There's only like, we can do whatever the hell we want to do. We can mutate structures, just as you use, like, for example, in an actor in Akka. We can mutate the hell in here because we always know it's always going to be the same thread touching it and only one thread. There's never going to be a concurrency in there. So we start out with the Scala vertical as a basic thing. Then we have this method, start future. This is basically like the first part that's actually being generated. So there's a start method and a start future method. There's a start method that takes the Vertex async result, or I can have it return a future, which is being generated, so we get a more Scala style of flow in here. The first part here is defining my REST API. Oh, well, I don't know, HTTP API. Let's be strict with that one. What I do is here is like I use the Vertex web project, which provides me with this facility to create routers. Like I can do like get, post, I can define all sort of routes. And what I also get is these nice handlers. Again, this type I have a so-called static handler. The static handler allows me to have static content. This actually means check if on the class path there's an entry web root React folder or on the file system. You can configure even more to have like live replacement and all that stuff, but that's the basic things. So if I give this to production, I package simply the static content with the application, it's going to be resolved there. The other part which is the interesting one, is this one, because this is what we're going to be using extensively. I told you about the event bus being used inside the JVM and across a clustered network of Vertex nodes. Well, we can extend it into the browser. So that means that like not only can verticals communicate with each other, but the browser can send and receive events from the Vertex cluster. This happens down here. This is just like I use these bridge options, and you see here I can, just like a firewall, like these are the most primitive ones. Normally, like if I open the browser bridge, it's locked down. It won't let anything through. I here allow that like messages addressed to browser can leave my network, and that messages addressed to server coming from the outside are also let in. There's deep filtering possible. You can do pattern match. You can do all kind of things in there. I just picked the most simple ones to showcase that you have these firewalling functionalities. So this is what I do up here. So first, like I have this alive probe. I serve my application and I allow this the React application running in the browser to connect back to my Vertex cluster in the most simple way. The next part is where things get interesting. This is like each vertical has a reference to the event bus. The event bus is like the nervous system of Vertex. In this thing, I create a publisher. Publisher means like if I take this I call it sender. I should change this later on. So like each time I use the sender, the messages I send through it are actually going to be published to browsers. So basically, this is my communication path outside of the cluster. So and what I do, what's the next step is then I also register a consumer, as we said down here. So the vertical wants to receive messages addressed to server. So these are basically coming from the browser right now. I convert it to a body stream. We don't really have to know. This is just like some syntactic sugar to get rid of some information I don't need at this stage. And then I register a handler. So, and now you have to kick in the brain, because right now what we're going to do, like each time we receive a message coming from the browser, we want to verify this message. So we're going to send it somewhere else, ask this part, is this message okay to be displayed? If we get a positive reply, we're going then push it out to all the other receivers. So what I do is I send it to the profanity check. And at the moment, when the profanity check completes, it means like I've received the reply from that profanity check, I check, is this okay? So like I just give the message out that has been in there. If I receive a failure, that means like the other side did not answer to my reply, I simply just say, well, Big Brother isn't watching right now. And down here, the last part, I create an HTTP server. I register my request handler, and then I just let it come up on the port. I prepared a little the demo itself. This is basically an SPT project, and I ran SPT Docker before, and I pushed everything into my local Minikube. And now, please keep your fingers crossed, because like on Mac, with switching networks, it sometimes messes up the Minikube. So first thing, let's check if Minikube is up. So yeah, great. So this is a little small. We receive this message like nothing is there. So first thing we do is we deploy the application. So what happens right now is that we are going to get So I hope you know Minikube. Like it's a great way of trying out Kubernetes locally. On Mac, it's basically just brew install Minikube and you have a full Kubernetes running. I don't like the Docker stuff, so like I normally go with that stuff. So what we see right now is like I deployed the front end node. It's already set up in here, and right now I should get a different reply if I go back to my thing here. No, it's not yet done. Starting up. Sorry, it's a little slow in here because I have a little trouble with my DNS. So let's check. You're gonna see a lot of stack traces. This happens because the DNS is stuck. Oh, it's now done with deploying. Oh no, because like what did I forget? Like I just deployed the service. I forgot to put ingress in there. I hope you guys have at least a little note. Just Google Ingress. It's basically a facility that allows, it's like a lightweight API gateway based inside Kubernetes that allows like to have things going together, and get the API together. So what I have to do is I have to add my ingress to publish the actual service. So, but now it should be up. Please, my friend. Yes. Yeah, that's the tricky part if you do it like in multiple steps. So right now, like we got the chat up and going. So I just want to say hello. No, hello world. We're international. So Big Brother isn't watching. Yeah, obviously. Like I just deployed the front end. We saw the rule just in there, so it wants to check if this is actually okay, but there's nobody there to actually validate this thing. Now we have to step in 9 minutes to the things that have to happen next. First thing I have to show you is we're now going to use Hazelcast. So Hazelcast is like you probably know it as a cache, but it's an in-memory data grid that is basically used from us to distribute the list of nodes that are part of the network. What I have to do is just to activate this functionality is have like the auto discovery for Kubernetes, which is part of Hazelcast activated, and then tell Hazelcast how nodes are marked. So I can have a selector, and I expect this to be part of my deployments. So let's check this. We just deployed something. And there it is. So here's the associated label. This is a great functionality inside Kubernetes. So I added this label to my servers. Before I deployed the Hazelcasting, that means like all services are now announced to each others when they join the network. So now we want to see how this thing works to have like a separate deployment, because we might have a high rate of incoming profanity being filtered. So we split this functionality out. So we have the front end deployed, now we need the profanity filter. So this is the filter vertical that we have right now. The filter vertical itself, it's also rather simple. It has a few other features that Vert.x provides. First of all, I hooked it up to the configuration management inside Kubernetes. That means like I get a live stream each time a certain configuration changes. I can react to those changes. In this area, I want to get a config map, which is called the profanity config. I retrieve it, I get it, like I split it, and then I apply it. And down here we see like the profanity check we saw from before. So this is the part that's going to receive the profanity check request. It's going to simply check. I did like a very crude thing here, just to see like if any of the words in this in the sentence I just received is part of our block list. If so, if it's not, if it doesn't intersect, it's just going to send back. And as a little helper, because I'm going to show you something, I'm also including the hash code, so I see like, okay, this is like by this instance. Otherwise, it just replies with a censored. So, as you might note, right now we have an empty set. So the first thing I'm going to do right now is deploy the actual thing. So first of all, like what I left out here is it's a separate Docker image inside the cluster. So they have no relation right now aside the event process side. So I deploy this whole thing. You can again take a look right now into the deployments here. We see we have a new deployment. The backend is right now in there. We have associated with the backend certain pods, and there things are running. We can again look at the logs. We take the logs from the backend. Again, don't be scared with the thread dumps. It's just like the checker, because we're stuck. We have to rely on some DNS code inside the JVM, which is actually blocking. There's already a separate library that I didn't use in here available. Let's see if it already hooked up. But what we see up here is this is basically the member count down here from Hazelcast. And what we see is, whoa, it already discovered the other machine running. So we have two members there. So let's check our chat. So now we get a reply. What happened? We have one instance of the front end talking to the profanity check via message passing. they discovered each other's automatically. Next part is, and now it's getting interesting. Now we have this event bus, they're connected. Like, how is this elastic? Now, the key thing is, I can just scale up my deployments right now. So I scale up the backend. It means like I give it 2 nodes right now. In the code, there's nothing telling it like how to handle the situation. The Vert.x event bus is actually taking care of it by applying a simple non-weighted round-robin algorithm to it. This is something we're going to have more flexibility in Vert.x 4, which like works just is about to start. But right now, like it's really just like you throw in your nodes, they get discovered through Hazelcast or whatever else cluster manager you use, and you can then start using this. And now, let's see if we're already there. Yes, we see like the last reply is just that we scaled up. Suddenly we have 3 nodes. And now we start sending messages. And we instantly see there's another hash code there. So this was answered by the new one. And this by the other one. So here we see the round robin. If and now, okay, so this is the part where we scale up. We can also scale down. But this is going to take a while because I think I don't have the. Now, the problem is this is going to take 3 or 4 minutes, and we don't only have 3 minutes left. And what I wanted to actually show you is how we now can control the filter list. Let's take a look at the filter list. I created a little YAML. What do we want to filter? Butterflies. Everybody hates butterflies. Cats. Cat and cats. I love dogs, so I keep those in. So, as you see, I use VI a lot. So now what I do is I create the config map. So let's do a little proof first. Hello cat. Well, works. Now I go in and pick my backend and apply my profanity config. Let's check again. Censored. And the cats are censored too. And if we go in there and, well, let's say like multiple cats are okay. We replace the config map, and now, because this is the one thing I did not test, so hello cat is still not allowed, and hello cats is now allowed. So what you see here is, first of all, we have full integration with what we have in Kubernetes. We can hook up with the config stuff. Kubernetes can do its stuff, which means it can react to failing nodes by creating new nodes. We can use elastic scalability provided by Amazon, by Amazon, Google Cloud, and all these. So we simply take the functionality that we have from this reactive framework, put it together with our infrastructure, and get magic happen. So this way of dealing with things has solved a lot of problems for me, because like a lot of the things that we normally have to deal manual with, or if you still remember building your own circuit breakers, building your own strategies of handling this stuff, this is all gone. We can just focus a lot more on actually building code that does stuff instead of fixing stuff. And since I only have 1 minute left, things I have left to say is, I'm downstairs. Ask me for whatever you want to know. We're reachable on the Vert.x mailing list if you have any interest on that. Hit me up on Twitter. I'm reachable there most of the time. And thank you for your attention. We have 57 seconds left for questions. So I guess one question we can answer. If like you have one question? Yep, back there. He was asking if I was sending this the config to Kubernetes config or to a service I made myself. This is actually Kubernetes config. So this is like the basic facility of config management in Kubernetes, because this is like what I want to rely on, because this is where my environment is defined. So it's nothing special. What we have there is just that that Vert.x is actually using this. So the question was like how actually the values get propagated into the application if there's like some direct invocation thing. The thing is, there are multiple ways. There's a service you can use. You can have environment variables be mapped to that. So normally like those things are also published as environment variables. What we use under the hood is actually accessing the Kubernetes config service because there we can actually listen for changes. So like environment variable is a little more static. You would actually have to reload the application because otherwise you won't see the environment variable change. But we are basically hooking up to the configuration servers and receiving updates there and propagating them those into the application. No, you can't. Like he was like monitoring the config map. The problem is you don't see the config map file. This is basically like I push it into the cluster, into the configuration management of Kubernetes. From there, Kubernetes distributes it. So you don't have this. I don't want to do that. This complicates just things. Like I have a service that actually gives me the. So like last answer because we ran out of time. Kubernetes has its own security facilities where you can limit access. So this is basically what you do. Like Kubernetes has good support for all kind of secrets and secret management. So for those things, what you normally do is like you group things being like either in a separate namespace or use other facilities to limit access to that. But that's private Kubernetes. So thanks everyone for attending. I have to take a picture. Twitter's going to be happy, and also my employer. So, thanks everyone for attending.